All right, guys. Today we're going to talk about the chemistry of life, or chemical bonding and water. So first, we're going to talk about chemical bonding. And before each lecture, I will try to let you know exactly what you kind of need to focus on before starting the lecture. And so today, when we're talking about chemical bonding, when you walk away from this lecture, you should know the elements that make up life and the types of chemical bonds and how they work. So, first, you might be asking yourself, why are we studying chemistry? And truly, biochemistry is the foundation of biology. And so we cannot truly understand biology unless we understand the molecules that are making up living organisms and the properties of those atoms and molecules and why they work together the way they do. Biochemistry really tells us, or really explains, why processes happen in biology. And so a good understanding of biochemistry is going to play into every single unit that we study this year. Usually at this point, I would show you a video of the bombardier beetle because it is a really good example of exactly how chemistry and biology mix together and how chemistry is really seen in biological organisms. And I will show this at the beginning of our next class and kind of start our discussion with it. So we need to begin by discussing the periodic table. Obviously, this is a picture of the entire periodic table, which will not be good for our purposes in biology. Luckily, in biology, we get to focus on just a few elements. So our most important elements are going to be carbon, nitrogen, oxygen, and hydrogen. And they are going to make up the majority of biological molecules. They are going to have the highest percentage of representation in those biological molecules. Phosphorus and sulfur are also going to play an important role. You're going to see them far more than you see sodium, magnesium, potassium, or calcium. Those are going to be seen just kind of in trace amounts in some biological molecules. So if you kind of want an easier way to remember this, you can think CHOMPS. That's a good kind of acronym or a way to just remember which of these are going to be the most important for biology. So remember that when we look at those atoms on the periodic table, atoms want to fill their valence shells. They want to become stable, and in order to do that, right, unless they're a noble gas and already perfect, they need to create bonds to do that. So they need either to get rid of electrons or they need to gain electrons. And so this tendency is what gives us chemical reactions, is what creates bonds, and what creates the biological molecules that we see. So remember, these atoms are either going to give up electrons or they're going to share them. And so let's kind of talk about some of the bonds that are going to be most important in biology. So the first type of bond we're going to talk about is that nonpolar covalent bond, which is going to be a very, very common bond in biology. And so in these types of bonds, our electrons are going to be shared equally by these two atoms. So in this example, we have a hydrocarbon, methane, where you have this carbon molecule and it's surrounded by 4 hydrogen molecules, and they're all bonded together, sharing their electrons equally with one another. And so what you're going to notice about these molecules are these types of bonds is that they're balanced and they're stable. They're really good building blocks, and a lot of the carbon-based molecules that we talk about, you are going to see these types of bonds. And because they're so balanced and stable, and because they're so strong, they're going to store a lot of energy. And so when these bonds are broken, they're going to release a lot of energy because it takes a lot of energy to break these bonds. Polar covalent bonds are going to be the next bonds that we talk about. Again, very important in biology, and really the most important molecule that we are going to see do this type of bonding is water. And so The reason why water makes this type of bond is because of the difference in electronegativity between oxygen and hydrogen. If we remember back to chemistry, oxygen has a much higher electronegativity than hydrogen does. So it has, it really has an affinity for electrons. And so these electrons that hydrogen and oxygen are sharing are going to be held just a little bit closer to oxygen. And because they're held just a little bit closer to oxygen, that is going to make water a polar molecule. It's going to give it this partial negative charge and this partial positive charge. The oxygen will have that partial negative because the electrons, which have a negative charge, are just a little bit closer to it. And the hydrogen is going to have a partial positive charge because the electrons are just a little bit farther away from it, from its nucleus. And so that's what makes those polar molecules. Hydrogen bonding so those covalent bonds were strong bonds. Those are going to be bonds that hold a lot of energy, are hard to break. But hydrogen bonding is a type of bond we see that forms between those partial positive and partial negative charges on molecules. And so we most commonly see this in biology with water. The partial negative on an oxygen atom is going to be attracted to that partial positive on a hydrogen atom, and then we see that hydrogen bond forming between those water molecules. And this doesn't just happen with water. It can also happen on OH groups in larger biological molecules, which we'll learn more about next week. The fact that this is a weak bond is important because it is so common in biology, because weak bonds don't take as much energy to break. And so a really good example of where we see this bond in biology is in DNA. And so you will find hydrogen bonds in between the bases of DNA strands. The fact that this bond is weak is important because that means it doesn't require a lot of energy to break. And so when we're doing biological processes like replication and transcription, it's not going to take a ton of energy to break those bonds between the bases to carry out those things. So molecular shape is very important when it comes to biology. The shape gives rise to the function. We can first see that in bonding. And so the fact that these hydrogen atoms are 104.5 degrees apart is what allows water to so easily hydrogen bond with other molecules of water, or makes it so readily available to bond with different ions. And so that's really important. And if you ever take organic chemistry, you will learn all about the geometry of these different molecules and why it's important for bonding and things like that. We also see that in hydrocarbons, and the fact that these hydrogen atoms are equidistant apart from the central carbon. This is called a tetrahedral formation. And really what it does is it just makes these hydrocarbons very easily connected to one another so that we can see those really long hydrocarbon chains. And so again, just the geometry of the molecule is giving rise to the type of bonds that it forms. A key point, though, in biological molecules is that the structure determines the function. And so your molecular shape on a molecule is really going to be important for what it does. So we see this a lot of times in hormones. And so hormones are little messengers in our body. They send chemical messages, and we will talk more about that when we get to chemical signaling. But here you have an endorphin, which is a type of hormone that has this configuration on one side of its molecule. And this area of this molecule is really important because it connects to channel proteins that send messages in cells. So pharmacologists realized that they could mimic this shape in synthetic molecules and get the same chemical signaling result. And so here we can see that if we have this channel protein, this is an endorphin hormone, and this is exactly how it connects to its channel protein so that it can send whatever cellular message it needs to send. Morphine can mimic the same job and send the same chemical signal so that it has the same biological effect. Okay, so we've talked about the chemicals that make up life and chemical bonding. Now we are going to talk about the properties of water. And so it's going to be important that by the end of this water lecture, you understand the importance of hydrogen bonding and how that gives rise to the properties of water, the unique properties of water that we'll talk about, how to interpret a pH scale, how pH can affect biological systems, and then why buffers are important. So if really the most important thing you need to take away from this lecture is that water is a molecule that really supports all life. Earth would not be the habitable place that it is if it were not for water. And so before we can talk about all the different properties of water, we just gotta kind of hit back as to why the chemistry of water is important. Water's ability to form hydrogen bonds makes it this sticky molecule. So water is sticky to itself, but it can also be sticky to other molecules. And that's going to be a really important feature as we talk about these properties of water. So the first properties we're going to talk about are cohesion and adhesion. And so when we talk about cohesion, really we're just talking about hydrogen bonding between water molecules, or water being sticky to itself. And so when water does this, it gives it this ability to have this really high surface tension, or have this ability to have kind of a hard surface. And so if we look here at this picture, we see a water strider. And the reason why it's able to sit on top of the water like that is because of that high surface tension, because it kind of creates almost a glass on top of the water. And so this is also why, if you think about it, if you go to jump off a high diving board, and when you hit the water, it might give a little sting to your feet. It's because of that surface tension, because your feet are breaking that water barrier, and it does have a little bit of force to it before you break through. Another example of cohesion is drinking through a straw. So just the water molecules, how they stick to each other as you apply the sucking force as it goes up the straw. And then adhesion is kind of like the opposite of that. So just water being attracted to other substances. We will see this in capillary action. And so the ability for water to move up really, really, really skinny tubes. We also see this with meniscuses. So we know, right, that's where you measure the water line on a graduated cylinder. And that's because the water is attracted to the graduated cylinder on the side. And so we wouldn't want to read it from that area. We'd want to read it from that middle part, because that's the actual level of the water. And so biologically speaking, or in terms of life, the most important way that we see adhesion and cohesion is through transpiration. And so transpiration is the evaporation of water from a tree or a plant, or anything like that. And so what happens is that, the roots take up water, the water travels up the stem or trunk of a plant, and it comes out through the leaves, through evaporation. And so the reason why water is able to travel all the way up to the very tops of the trees and to the leaves is because of that adhesion and cohesion in the xylem and phloem of the tree trunk. So another important property of water is the fact that it is a solvent, or it is able to dissolve other substances or solutes. And so the reason why it's able to do that is because the polarity of water surround positive and negative ions. So if we look down here at this beaker, which has salt in it, the water is going to slowly chip away at those sodium and chloride ions, and it's going to dissolve that salt. And how it's going to do that is it's going to slowly surround these ions. The positive hydrogens will surround this chlorine ion, and the negative oxygens will surround this positive sodium ion. And that's how it's going to create solutions, or salt water, a bunch of just sodium and chlorine that is dissolved in that water. And we'll see this too with other biological molecules like proteins. It might not be every part of the molecule that's interacting with that water, but different ionic parts of those proteins will do that. So what dissolves in water? Here we have hydro, meaning water, and philic, which means love, okay? So things that love water are going to dissolve in it. And so these are substances that have that attraction to water, and these substances we would describe as being polar or being ionic. What doesn't dissolve in water? Things that are hydrophobic. Again, water and phobic meaning fear, okay? So things that fear water will not dissolve in it. They are going to avoid water at all costs. They don't have an attraction to it. And we're going to describe these substances as nonpolar. These are going to be items that you're really familiar with, things like fats and oils. And if you look at the molecular structure of our fats and oils, you're going to see those long hydrocarbon chains. And remember, those hydrocarbons are bonded together with nonpolar covalent bonds. So there's no polarity in these molecules at all, which means they're just really not going to like water. So when you woke up this morning, you probably didn't realize how special the ice floating in the top of your water bottle was, but I'm here to tell you today that ice is very important. And so why is ice so important? It's because, we don't often think of this, but ice floats, whereas most solid substances sink. And the reason why they do is because most solid substances, molecules, are arranged in really tight patterns where the molecules just vibrate in place. Well, that doesn't happen with water. As water molecules start to slow down, their hydrogen bonds kind of become equidistant apart. And what that does is it forms this crystalline structure in solid water or in ice, which allows for these big gaps that you see and really spreads those molecules out so that it's really a less dense form. In comparison to liquid water, all of these molecules are constantly shuffling past each other and forming hydrogen bonds with other molecules. And you'll notice that the gaps between these water molecules are much tighter. And so it makes it so that these larger gaps will float on top of these smaller gaps, allowing ice to float. And so we might wonder, why is that even important in life? Well, it ends up being very important. So we know that our, larger bodies of water, they don't freeze solid. The surface ice ends up insulating that water below, so that in the winter times, Our oceans and lakes are habitable to organisms. And so if ice sank, then our, lakes would start freezing from the bottom up. And so if the water froze every year, obviously no fish would be surviving. And then in the summer, only the upper few inches of water would thaw, which really wouldn't leave much room for life in those months. And this also contributes to the turnover of lakes, or the mixing of warm and cool water, which really allows nutrients to cycle, which also can help to make it habitable for organisms. Specific heat is the last property of water that we're going to talk about. And so pretty much this just means that it takes a lot to heat water up, and it takes a lot to cool it down. It takes a lot of energy. And so really, this is why we see the moderate temperatures we do on Earth, and why Earth is so habitable to organisms. And so I think the best way to really explain this is if we look at temperatures between the middle United States and the coastal United States. So being in Kansas, we're lucky enough to live in the landlocked middle of the United States. And we know in Kansas that we see really high temperature extremes, anywhere from, 100 degrees Fahrenheit in the summer to, 0 degrees Fahrenheit in the winter. And so here we're seeing a huge gap in our temperatures. Whereas if we went, to Northern California, we might see summer temperatures ranging in the 80 degree Fahrenheit, but their winter temperatures are much more mild, only getting down to the 40s or 50s. And so we can see the difference there is really is really based on the fact that the coastal cities have those oceans to absorb that energy, to absorb that heat, absorb those cool temperatures, to keep the temperature on land much more mild. And so it just moderates those temperatures. And that's why, on Earth, we don't, see super, super, super high temperatures that won't allow life to live. And we don't see super, super, super cold temperatures that won't allow life to live, except maybe a very few places. The specific heat also leads to this idea of evaporative cooling, or that high heat of vaporization, meaning that, it takes a lot of energy to get water to go from the liquid state to the evaporative state. When it does, though, or when water does go from that water to vapor state, this thing called evaporative cooling takes place, or what is left is a cool feeling from where that water once was. And that is what's responsible for really cooling you down when you're hot. And so our bodies sweat or let off water to do this evaporative cooling, so that when our sweat evaporates, we are left with that cool sensation that cools our bodies down. So the last thing we really need to talk about is just pH, and kind of why that's important to living organisms. So we should remember this a little bit from chemistry, but the ionizing of water is what leads to pH. So if the hydrogen ions and the OH ions are equal, that's going to give us a neutral pH. If we have more hydrogen ions, then that's going to be acidic. If we have less hydrogen ions, then that is going to be a basic solution. And that gives us our pH scale. And so things that are low on a pH scale are going to be acidic, and those things that are high on a pH scale are going to be basic. And so in this graphic, you can kind of see just where different things that we would eat fall on the pH scale. But if we're looking at the difference, between a pH of 1 and a pH of 2, a pH of 1 has 10 times more H plus ions than a pH of 2 would have. And so that's kind of the difference. So as we go up, we're going to have 10 times less H plus, 10 times less H plus, as we go up the scale. And so why do we even really care about pH? Well, in biological functions and biological molecules, pH is going to be really important because that's going to dictate how our different molecules work, the structure and the function of those molecules, especially proteins. And so certain areas of our body are meant to be at a certain pH. Like your stomach, for instance, operates at a more acidic pH because it needs that stomach acid to help it break up food. Our blood, on the other hand, needs to operate at a more neutral pH. If blood becomes too acidic, that's bad. It could lead to death. If it becomes, too basic, then that will also be bad for us. And so something that helps to keep this in check are these things called buffers. And so buffers, they just minimize those changes of H plus and OH ions, and they keep pH stable. And so buffers are really important in biology, so that our bodily functions aren't inhibited by, an out of whack pH. And so I know you've all heard of acid rain before. This is something that all biological systems have to deal with, especially ecological systems. And so acid precipitation is just rain, snow, or fog that have a really low pH. And so this precipitation is caused because of pollutants mixing with the, water, the water cycle on Earth. And so, if acid rain falls, it's going to mess with the pH in different bodies of water. It can mess with the pH of soils. And, that's going to end up causing damage to the plants and animals that live in those places and can make them, almost inhabitable. And so just kind of something I want you to take away. And if you want a little more exploration into water, I really love documentaries, so I will recommend them often to you all. But this Netflix documentary is The World's Water Crisis Explained. It does a really good job just kind of talking about day zero and how, we don't really treat water on this planet like the commodity that it is, and what's going to happen if we run out of it. And in Kansas, a lot of farmers in western Kansas are draining the Ogallala Aquifer, which is one of the biggest aquifers that the state of Kansas sits on. And so this is just kind of an interesting little documentary that I would recommend that you watch if you have time. Maybe you've already seen it, but definitely worth the watch. And so pretty much what I'd like you to do is just write down any questions you have and bring those to our discussion tomorrow. It's going to be really important that, you just take the time to really figure out what you still are questioning or what you might not quite understand, so that we can discuss that as a class tomorrow.